works go over a range of problems from geometric flows and interface for material sciences, which I learned long before, and then more recently pattern formation and non-localized isoperimetric problems, as well as the work that is Alama equation, many more. Nella di adesso aussi fellow della Société Mathématique du Canada. Please, we have a talk from the property on translation. Working dans les copolymer, triblock, double bout et un problème de partition.
Merci beaucoup. J'aimerais beaucoup remercier donc les organisateurs du colloque des sciences mathématiques du Québec, en particulier Alina, Giovanni et Guillermo pour m'inviter. C'est un grand plaisir d'être ici. Je vais commencer en français, mais inquiétez-vous pas, ceux qui ont des problèmes, j'entends. Je vais passer, malheureusement, si on peut dire, à l'anglais parce que j'ai des problèmes de vocabulaire dans ce domaine. Et voilà, donc on va passer à l'anglais sous peu. Donc, c'est des travaux joints avec Stan Alama de McMaster. Et il va y avoir vraiment deux directions. La plus grosse direction, c'est sur le copolymer. Je vais vous montrer toutes sortes de comment dire, phases intéressantes que j'appelle des doubles bulles ou des anneaux. En anglais, c'est double bubble ou core shell phases. Mais aussi, je vais finir avec un problème de partition qui sort de ces problèmes ici. Et ça, c'est avec notre étudiant de maîtrise Silas. Alors que pour les copolymers, c'est avec Xingyang Lu de Lakehead, ici en Ontario, et Chong Wang de Washington and Lee University. OK. Donc, ça, c'est parce que c'est un colloque. Donc, we're starting with cute little picture of pattern formation. We see some stripe patterns and some what I call bubble, as we're going to see, single bubble patterns. And to model this phenomenon, one sees what's important is to have a locally attractive. Le français peut durer longtemps. Exact. C'était le titre. One says, so a locally attractive term and a long range, or in fact, non-local term that promotes separation, fragmentation. And so that's how you end up with these fragmented stripes or bubbles here. So this is called copolymer, triblock copolymer. So right away, I'll show you what it is. There are three phases, A, B, and C. They are repelling, but attached. So it's unhappy couple, if you want, or triple, or whatever you want to call it. So these three phases, they don't like to be together, but they are bonded. And so depending on the mass fraction, and now I have to start using the mouse, on the mass fraction, meaning how much of A, B, and C there is, respectively, you get different patterns, different morphologies. This one on the top left is precisely a lamellar pattern, and this corresponds to all masses being the same. The A, B, and C, same phases, same masses, but you can have other shape. And here, actually, we're going to see that this is an example of a core shell. We're going to see this as we go along the presentation.
So you have a division between fragmentation and concentration.
Yes.
Now, what is A, B, and C here?
So it's a three phases. So this is a triblock copolymer. There are three phases, and precisely it's going to model. It's three different monomers. So it's called A, B, and C. It's three phases in your
with the same material, it changes across the temperature or pressure.
No, it's three different material. Three different phases of the polymer attached together. So it's three different phases, and they correspond. So to model this, we use a potential typically, which will have three different minima, and each minima corresponds to the pure phase, phase A, phase B, phase C. Those are three different materials glued together by whatever way, and they are bonded, and so you have to keep in mind.
Exactly what we call phase in physics.
It is not, no. You could think of, yeah. So I'm trying still to give some names so that we see phase A, phase B, phase C. But it's three different material glued together, but at a macroscopic level. And so to model this, We are going to work in a periodic model, so I have to spend some periodic domain. I have to spend some time on the model. We are, for each of the phases, pure phases, or the region omega-1, omega-2, omega-3 are the ABC phases. So we associate vector order parameter to the system. And we saw that the mass had to be prescribed to get all these phenomena. So we impose some prescribed mass to each of the phases. And so I'm writing the energy. Don't be frightened. This energy, we're going to study it all along. It's going to be decorticated. We're going to understand every single thing by the end of this lecture. The first term is nothing else than perimeter. So think in 2 dimensions. We have different region of A, B, and C phases. That's what you have to keep in mind. And there is some interface between different regions. And so the first term measures the length in 2 dimensions, or the surface in 3 dimensions. And it is weighted by surface tension. So I quickly said that this is coming actually from a diffuse model for people who are comfortable. This is really a sharp interface limit of a diffuse model in which you would have a gradient squared, a Dirichlet energy, and a potential. This potential would have 3 minima for each of the 3 phases. And when you take what's called a gamma limit, some convergence, some singular limit, if you want, you end up with this energy. And that surface tension here is actually a kind of a Riemannian distance. It measures in the potential level, if you want, the potential shape. It measures the distance to go from one minima to the other. And so there's a very natural inequality that must be satisfied here, because the distance to go from phase, let's say, A to C should be less than A to B plus the distance to go from B to C. So there is always this inequality here that must be satisfied. And we're going to see the effect of this surface tension here on what the minimizer, we're interested in minimizers of this energy here, trying to understand this pattern that we saw earlier. What about the second term? So the first term is local. It's just we're weighted perimeter. The second term is the non-local term. That's a repulsing term in 2 dimensions. Think of it as a log of the distance in 3D of your Coulombian potential. And again, there's many parameters in these problems. There was the surface tension. We're going to see its effect on the geometry of the limiting problem. And there is the interaction coefficient here. So this is a weight in front of the perimeter, and this is also weight in front of the repulsing part of this energy.
So, you say that for to define sigma ij, you have z of 0 is equal to AI.
So that's my two, yeah.
So because it is value in R3, then we have to understand that AI and is it A or alpha?
It's alpha I and alpha J.
Alpha, okay.
Alpha I and alpha J are
Okay,
points.
it's not A.
They are points. They are points in your domain, corresponding to the minima we associate of the pure phases. And so this is your distance naturally coming in these problems. In fact, what people know, Allen can converge to mean curvature with exactly the surface tension term. If you are just 2 phases, it's some particular constant depending on the potential. Okay, so in this talk, we're considering of what's called a dilute configuration. So remember, we have 3 phases. I'm going to assume 2 of the phases are very small compared to the third. So we're going literally to have a C of the third phase and 2 small phases, and we're going to figure out what do they form as a pattern. This is following some work by Rostom Truxy and Marc Pelletier. They worked on diblock, so 2 phases. They didn't have the vector value constraint here. We have to work. Sorry, Pelletier just 1L, yeah. And so what they did is they introduced, I said it have to be very, very small. So they introduced a small parameter. This is the eta parameter. We're going to come back to it later on. And so they are rescaling here the mass so that 2 of them are very small. 2 dimension is eta square and 3 dimension eta cube. And you need to have a strong non-local interaction so that both terms, the local and non-local, will interact and give us pattern formation. Okay, I'm going to discuss that more. So first, let's discuss the isoperimetric problem. Okay, that's the because we, as I said, we're looking at local problem. We are going to really have to do a blow up to figure out what the small phases look like. So the isoperimetric problem is naturally posed for this problem in R2 or R3, in R2 or R3. And so we have again two phases of given mass M1 and 2 fixed. This has been rescaled to be fixed now. And we're looking at this perimeter, weighted perimeter problem. And we're wondering what the minimizer of that look like. So now we are, forget non-local, local, just this, isoperimetric prime in R2 or in R3. And so case of equal surface tension. So we're just summing the perimeter of the different phases. This was actually discovered recently, 1993, in 2 dimensions. This was called, in fact, the double bubble conjecture. You fix 2 masses. What is the minimizer of perimeter with those 2 masses fixed? Is the double bubble with the equal, when the surface tension is the same, the angle we have here at the junction here, 120-degree angle condition. The difference between those 2 pictures that the masses here are the same. Here, one mass is bigger than the other, but the angle condition is still equal to 120 degrees. And they proved this. So the first in 2 dimensions, this was proven by undergraduates. So it's impressive when you're able to get undergraduate to solve some important conjectures. In 2 dimensions, undergraduate working with Frank Morgan, they proved it that this was indeed the minimizer.
So your bubble is not flat. I mean, kind of minimal surface.
It's
minimal surface.
Exactly, you can think of it as in 3 dimensions as your soap bubbles that was studied a long time ago.
Pressure is different.
Exactly.
It's not the kind of minimal surface.
Exactly. But think of it. So the surface tension here is really a weight in front of the perimeter, right, or the surface area. It's not the pressure or whatever. And in 3 dimensions, this was proven by Frank Morgan and collaborators. And we're going to come back at the end to these isoperimetric problems. What about if you have a strict now inequality in your surface tension? What's the effect on the minimization problem? Well, Lawler proved about the same time, a bit later actually, that in this case, the difference is you still have double bubble, but different angle condition. Instead of 120, it will be weighted. As you can see here, the angle will be dependent on the surface tension. Okay, and this was indeed proven. And so we see, right, the difference between those 2 pictures is just the difference in surface tension. That's why in one case, it's a bit more inside, and we're going to really see that very soon, the effect of the surface tension on what the minimizer looks like.
The minimizers are they minimum, or they could be critical?
They all are minimizers. They all are minimizers.
And we have a minimum.
In this case, they are global. They are global. Yes. Yes, in this case, yes. What about the case of degenerate? Right, in the case where the surface tension between the phase, external phase, let's say 0, 2, is equal to the sum instead of being strictly less. That encourages the phase 1 to be between the phase 2, I'm going to have pictures soon, and the outside, because the surface tension is just the sum of, are related this way. So minimizer in that case, you're going to have therefore some region, omega 1, I'm calling it, between the inner and outer region. So this is an annular region, we're calling it core shells. And this is good because we have a picture. Core shell is just defined, you're given an inner disk and an outer annulus. That's your core shell. So this is the picture here that you should keep in mind for core shell. This also, by the way, is a core shell. You could have, these 2 have the same perimeter, solve the same perimeter problem. One happens to be tangential, one happens to be inside, but they all give you the same. So there is some degeneracy in the geometry problem. And what about all these pictures? This is precisely to show what happens as you increase the surface tension. So the first one here is equal surface tension. 1, 1, 1. So we don't have this. It's not the degenerate case.
And you might be involved with the tension outside of the unit.
So the blue is 0, and then 1, 2, exactly. And so as we're increasing sigma 0, 2 from, again, 1, 1, so everything is equal, we are increasing the surface tension between 0 and 2. The 2 phase being yellow in this picture. So we have a bigger weight here. So we want less perimeter of the yellow phase compared to the blue phase, right? So that's why it starts entering here. And by the way, this is a double bubble with the angle condition we said depending on the surface tension. And so as I'm increasing 0,2, you see the yellow phase here enters because you want less and less of the minimum, the perimeter. And you end up, when they are equal into these two cases, we're going to see that this geometry, in a sense, degenerate. Both are minimizer. We're going to resolve the degeneracy when we add a non-local term. Actually, it's going to choose what is better, depending on. Now, remember, we are just discussing here surface tension coefficient. We're going to have also interaction coefficient entering soon. Yes, I already said that. So I'm adding now the non-local term. So the non-local term I told you is pushing everything. It wants to push away. It wants to fragment the phases. And here I'm just showing, what are possible configuration. We're discussing about critical point. So there were some earlier results I'm drawing here the case of equal surface tension. They Ran and Wei were able to construct via a complicated Lyapunov-Schmidt type argument. We're able to construct critical point solution to our Lagrange equation, which gives you here an assembly of double bubble. That's the typical double bubble. But with our so Chong Wang was our postdoc. She was a student of Ren. They also could construct assembly of core shells. So those are the two geometry we're going to see soon. And of course, if the surface tension is, if the interaction coefficient is too big, the phases want to split, and then you have single bubble. So the last one is really there's too much surface interaction coefficient. They don't want to be together. We're going to see when we get the first two. And our question we will address is what the global minimizer we are reducing to 2D now look like, again, in the case of two small phases in the third phase.
How should we see or understand the motion of A, B, so the A, B, and C? That is, it seems that some viscosity, or what, that in your models, things can move. The bubbles can move, and therefore, what is the constraint for moving?
No, it is more, it's a degeneracy, literally. It's a degeneracy. It doesn't move the double bubble, it's prescribed. It's prescribed, right? Once we know the surface tension, we know the double bubble. The core shell one. There's no dynamics here. It would be nice to do dynamic, but we don't have it yet. So this is hard enough as you're going to see.
Yes.
There are some dynamics, by the way. We're going to see some movies. This is first time I can show movies, first subject for which I can show movies. We're going to see movies soon. So let's try to understand, as I said, what happened when you include a non-local term. So we're going to do this, what I call the dilute regime. So I'm being more precise now, a bit more technical. Don't worry if you don't want to understand technical. We're going to go soon to nice pictures. So we introduce, as I said, a small length scale parameter I'm calling eta. We are asking that two of the phases, I'm just repeating exactly what we do. Two of the phases are at mass, very small mass. I'm in 2 dimensions, so it's eta squared. I have again rescale appropriately my order parameter. And as I told you, we have to choose. I'm not even writing it. It's a choice that you have to make. Appropriate scaling for the surface tension and for the interaction coefficient in the scaling, right? I'm looking at the small scaling eta tending to 0. I have to rewrite the appropriate critical scaling so that we get both the perimeter term and the non-local term in the energy when we look at minimizers and consider the limit as eta tends to 0. Small droplet, right? Small phase. So small mass. We're looking at minimizer of this rescaled energy. It's the same as before, but now with the appropriate scaling being imposed. So the beta here is, the beta is related to the surface tension that we discussed earlier. So that's the setup. Again, this is the most technical part, really. It's our result on minimizers. So we are able to show, we're looking at minimizer of the energy as eta tends to 0. We're able to show up to subsequence that as eta tends to 0, minimizer will decompose. So you will have these what we call clusters. There will be finitely many, this is not easy to prove, finitely many clusters for minimizer, finitely many of these clusters. They will not converge to each other. They are at a distance apart from each other. And if you blow up around each of these clusters, that's when you end up with the geometry problem we discussed, right? So we blow up around it, and we see that, for example, here I drew the case where the surface tension are equal, so we see a double bubble, right?
So maybe I would suggest to change the word blow up.
What's wrong with blow up?
Because you do assume.
I do.
Blow up is not mentioned in algebraic progression.
No, in analysis, in PDE, we're using blow up exactly in that sense. It's a zoom, it's a zoom, it's a zoom, but blow up literally means rescaling. It's literally what we use. Yeah, it's a rescaling and yes. Okay, so that's what minimizer look like. So we said that we are not surprised in a sense that when we blow up around this point, when we zoom around these points here, that they look like the perimeter problem we discussed earlier. But there's a question of where are they located? What's the distance? How many of them are there? And that's what the non-local term determines. So once you add the non-local term, so I'm just repeating here what I said, they minimize the perimeter. Once you add the non-local term, you can rewrite the energy. You can see the energy as we prove a finite sum. So there's finitely many of these clusters. And each of the clusters, when you minimize, we're going to minimize this energy. We're looking at minimizer. It's going to choose, and this is a minimization problem, of how many masses, how many droplets clusters do we end up with? And we see this very clearly in this limiting energy. This term here is the contribution of the non-local term. This term here is what it comes from the non-local problem. And we see, therefore, a quadratic term in masses. That means that you don't want big masses. We're trying to minimize this. But we have to show that they can't be too small either, because if they are too small, there's infinitely many, right? So we're able to control, it's not easy, indeed, that there's finitely many decomposition. So that's what I'm writing here. The effect of non-local is reflected in the quadratic dependence. The minimization problem is we're assuming infinite decomposition and find the masses that decomposes properly the non-local perimeter problem. I'm coming in a second. And so we see that for large mass, there will be a separation, but we should not too many. Yes.
So I have a question. How do you know that each of these
clusters or droplets,
clusters are the same?
That's because once you're given the surface tension, we can prove that determines the local geometry of each of the droplets. What we are not able to prove, you're asking a very good question, is they're all exactly isometric. That we're not able. Yeah. We can show they are double bubbles because of the local perimetry problem.
Because of the surface tension constraint.
Yes.
You also maybe know that the mass cannot be, the energy cannot be too small for this clusters.
It is exactly that, and it's much more difficult than the droplet regime because we don't have convexity or concavity. Yeah. It's a very complicated. We don't have anything explicit about the perimeter for double bubble. Nothing in terms of the So it's much harder to prove it, but we are able to prove it.
Yeah. So actually, this is true on the assumptions of, I would say, homogeneous and isotropic.
Right now, everything is isotropic, and we are in a
homogeneous because locally, I mean, you have
everything is homogeneous and isotropic.
Because locally, you have always the same order. There is no local imbalance.
I mean, strictly speaking, with the surface tension, I actually have some non-isometry, right? With the surface tension. Yes, so it's not totally isotropic. Yes, so it's not totally isotropic. It's included in the surface tension. But it's homogeneous. I have no X dependence on my coefficient. Yes, yes, it's constant. It's already hard enough, as I said. Okay, and this was for minimizers. We can also obtain a gamma convergence result, actually, for any finite energy configuration, so corresponding to your also critical point. But it's for minimizer we can say a lot. And
So you said that it is not isotropic, but it is isotropic. But then
no, the surface
does
tension.
it mean that the bubble has to be oriented in some way?
Oriented. We're going to see. We're going to see a.
It could be.
We're going to see a picture soon.
Okay.
We're going to see a picture soon, and it's via a higher order gamma order in your expansion.
About polarization, actually.
Yeah, we're going to see. You can think of it a little bit as droplets, but no, not really. Okay, so and we're able to see. I was asking where would the droplets will be located. We can obtain a renormalized energy that will, but to minimize it, you see where the droplet should be located. And as I said, this minimization problem tells you what the masses are, but we're going to see that the interaction coefficient now, what is its role in choosing those particular decomposition into small masses. And first movie, here we have surface tension which are equal. So therefore the isoperimetric prime wants double bubble. And we're able to prove that if you're, again, this is interaction coefficient between the two small phases. If it is too big, that's what this says here, then they will only have single bubbles. They cannot stay together. And we're proving this. And this is a movie, by the way, I'm showing it.
Small compared to the ambient.
The gamma 1, too small compared to, so there's a critical interaction coefficient. If you're above it, then you will end up being only single bubbles. And here I'm noticing that, so this is random, so this is movies made by Chong. She starts with random initial data, take a graded flow actually for the energy. And so that's what we saw it moving and eventually going to a minimizer. Notice here that we would have expected.
It's quite nice.
So notice that, so because so it is the non-local term that decides which distance there should be between all these minimizer. You would expect actually the hexagonal type pattern, and there are, depending on your coefficient, here's an example where you end up with a rectangular lattice as opposed to your usual hexagonal lattice. For particular choice, most of the time it's hexagonal. So this was single bubble. When you get double bubble, well, the interaction between the two small phases should be small. And that's our result here. First result, there are several results we obtain here. And first result is if your mass is not too big and your interaction coefficient between the two small phases is small enough, then you have exactly one double bubble, the minimizer, exactly one bubble. That's because my masses are small enough. But in the case where the interaction coefficient is 0 between the two small phases, we are able to construct all sorts of minimizers. We're able to show, given any number K1, K2, I can find masses, M1, M2, global mass, try the minimizers at least K1 double bubble and K2 single bubble. And in that case, the single bubble will all have the same mass. They will all look the same, exactly the same division, and that we're able to prove. And only if there is some single bubble, it has to be the same phase. It's just that one of the phases is bigger than the other masses.
In this case, I think the yellow single bubble.
No, it has changed.
It's the same.
Right? It's sorry, and so it should be as opposed to before. It should have been yellow and red with black with blue outside.
But what I mean is
sorry.
The small yellow and the blue should. I mean, you see, the single bubbles are just blue.
Yes.
But they could be also.
No, that's my point. So we are able to prove that the only way to have single bubbles is if there's too much mass of one of the two phases, and that mass becomes the single bubble. Yes, it's exactly that. And that's what the picture shows. That's when you have coexistence.
Sorry, I didn't.
But you couldn't. I said it. You're not supposed to be obliged to read my slides to figure it out. That would be sad. Yes, so when there's coexistence of single and double, the single bubbles must be of the same phase. And so there has to be a large enough excess of one phase compared with the other. And we're able to prove, as I said, that the single bubble all look the same. Another movie. But we expected when actually question is there are lots of open questions in this direction here in this set of problems. We expected that there should be some region where minimizer must all be form of double bubble. That you choose appropriate mass, appropriate interaction coefficient. And this is precisely some choices or parameter where we see, as we can see here, I mean, slowly by slowly, we see that we end up with just, yes, there, only double bubbles. But notice more. There's actually something here happening. They continue, we're still not at the minima. This is still, the gradient flow is still moving. Notice what's happening here. This is really fascinating from my point of view. You see? You see? They all align. There's kind of a they all align. And this is something we expect to see at the third level of your gamma convergence expansion of the energy. So we have not been able to prove this. This is open for the public, for the world, if you want to. Okay, what about core shells? We've seen single bubble, we've seen double bubble. What about core shell? We saw that, well, first I'm kind of telling you, we suspect that there should be often core shells, actually, because we saw the picture of a copolymer. It was A, B, C. There should always be some B between the phase A and C, since they're attached as well. And so we suspect that there should be some penalization for the 0 to 2 phase transition. And I remind you, this was the picture that we saw. Notice, this is some, pictures done by physicists. No double bubbles here, right? So we suspected that we should look really at the degenerate case. That should be the most appropriate one, in fact. So we are back to the degenerate case, in which case we know the minimizer for the local problem are core shells, right? And so here's a video again.
So the equality means that you are perfectly Euclidean,
yes.
Euclidean space.
We are perfectly aligned.
Sigma 0 2 is equal to sigma 0 1
plus sigma, yeah.
That you are
aligned. Yes, exactly.
That's actually a way to define Euclidean.
Yes, yes, yes. That would have this property. Yes, 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 yes. So this is the video where we see indeed. So she has chosen a certain parameter, in particular, the interaction between the two small fishes should not be big, right? Because if it's big, they don't want to be together. So in this picture, the interaction gamma 1 to 0, the interaction is very small. But we have the degenerate sigma 0 to equal the sum. So we end up with indeed double bubble. And notice they do form now in your hexagonal pattern. That's where the location is, and that's what you would suspect often. And now this is where we would like to figure out. Notice in this picture, they were centered. It was literally an annular region. And it turns out that to figure out if your core shell, we are able with the non-local term to figure out if the core shell should be tangential, the inner disk tangential, or centered. Due to the non-local term, we have to look at what's called a second gamma limit. So I'm subtracting here the energy, the limiting energy at first order, rescaling appropriately. Don't worry, we get some energy at the next order. Again, don't worry about this. This is the term that will be dominant. It's called self-interaction term. Let's not worry. Here's the proposition. In case of the degeneracy, sigma 02 is the surface tension, is the sum of the other two with given mass. If the interaction gamma 1, 2 is smaller than gamma 1, 1, the other the self interaction for one of the phase.
If gamma 1, 1
is bigger, so if gamma 1, 2, the interaction is smaller, is small enough. Well, basically, they can be together, two small phases, and then you expect we can prove the minimizer is concentric core shell. Right. But if the again interaction is too big, while not being huge, they can still be together, bigger than gamma 1, 1, the interaction for the one of the two phases, the phase which surrounds it. Then the minimum is attained by a core shell, which is tangential. The inner boundary is tangential because they don't want to be together, right? So they are pushed. They push itself to be.
Now let's see why you use the word phase.
Now you see, yes, there's lots of phases. Okay, yes. We have not done that. So here's a summary of what we've seen so far. Before we go to, I promised a partition problem that is coming from all of this. So here we started, remember, this is the case where all surface tension are the same. We had double bubbles. The surface tension is increasing. So one bubble, the yellow phase enters. Eventually, when it's degenerate. Oh, this has low battery, by the way. So this computer will not last very long here. And then my talk will disappear. And I want to show the partitioning problem. So I don't know what the problem is. Very good, very good. This is not, she does not, now it's green. Perfect.
No,
That's great, perfect.
electricity.
Yes, now it's good. I can see it. Okay, and then I'm increasing now the gamma 1,2 term, right? As the interaction term between the two inner phases increases, again, we see that the inner bubble, the inner yellow doesn't want to be inside anymore, wants to be tangential, and eventually even leaves because the interaction term is too big between the two phases. Okay, so partitioning problem. Okay, we're going to see the connection in a second. This is a colloquium, so, and I do have time, fortunately, actually. I was worried with the time, but now I can relax. Yeah, I can relax. Colloquium, so what is your classical partitioning problem, classical isoperimetric problem? Find the shape of given area with the smallest perimeter. Very classical, solved by Zenodeus in about 300 AC. And really, it's some Greek writers who said that he had resolved this and how he had resolved this. It's not, he didn't write ever an article on this at the time. The answer is the circle, and he did it by comparison with polygonal shape at the time. That's what he thinks to do. Much more recently, 1850 now, Steiner realized, well, this is not rigorous. What type of rigorous proof is this? So he introduced this very, very nice Steiner symmetrization and proved that, and this is the fun part, if there is a solution to this minimization problem, if it exists, then it must be the so-called using symmetrization argument. But the analysts of the time were like, what do you mean if? What is this? So Weierstrass entered the game, if I may say, and using a kind of, using calculus of variation, introducing this idea of isoperimetric inequality, he proved there is a solution, existence of a minimization prime analytically. And then with Steiner, we know it must be the circle. So this, of course, led to natural extension. And we've seen one, the double bubble. Instead of having one given area, now we're giving a pair of planar region in R2, I'm doing it in R2, given area, and we want the combined perimeter to be minimized, right? So this was the double bubble conjecture, that's what we expect it should be. And we've already seen this cute little...
The
sum of the two.
The whole volumes.
Exactly. And they were able to show that the sum of the perimeter is minimized when you have these double bubble shape. And we've already seen meeting at 120 degrees. Here, my surface tension are all the same. We've already seen this was proven earlier. Then, of course, you could ask, well, why 2 regions? Why not 3 regions? But by the way, as you increase the number of regions, it becomes very complicated to study. And so this was proven by comparing 54 different cases. I mean, this was very complicated by Wishiramala in 2004, that in the plane, when you have 3 regions, it's the triple bubble. And I'm going to have a picture soon. Then 2008 and 2014, in any dimension, prescribing 2 area, minimize total perimeter, it's still the double bubble. And you can see even but still very complicated. Very recently, now it's this year, 2023, Millman and Niemann were able to prove that it is double bubble in any dimension. So that was different proof. The triple bubble, dimension bigger than 3, and the quadruple bubble for dimension bigger than 4. And in all cases, if the number of region is less than dimension +1, the minimizer must have spherical surfaces. But that's it, that's the level. We cannot do right now better than this. And I have a picture here to connect to my copolymer. You remember we had the double bubble came up as the geometry problem, the local geometry problem. when we had 2 small masses in a third. So if we had 3 small masses, now we're looking at quadruple, right? 4 phases. So we have some result as well with Xingyong and Chuang. In the case of tetrablock, with 3 small masses, well, what a surprise, you end up with the local isoperimetric problem for which the solution is the triple bubble. And at the same time, I have a cute little picture what the triple bubble is. But then that introduced a new problem that we had not thought before. What about, back to triblock, there's just only 3 phases. What if one is small, 1 small mass in 2 big masses? 1 small mass, 2 big masses. Well, in that case, these 2 masses, how will they want to separate? They will want to form what we've seen before, lamellar patterns. And your small mass will want to be, actually, we're trying to minimize, remember, local perimeter plus non-local term. Your small, tiny droplet will want to align properly in a way to minimize perimeter. So this is a picture. They will align on the lamellar strips. That's a picture, numerical again, numerical result. And if you do a blow up around that, these little lens, we call lens shape, if you do a blow up, what we expect is to recover what's called a vesica piscis in Latin, which is fixed. So again, you have 1 fixed mass in 2 large ones, right? And they must meet, you expect, as in the picture coming up here. So we have this small mass here, let's say mass 1 given. I mean, remember I've done the blow up now, right? So this is mass 1. The angle condition here will be 120. And here I have 1 infinite area called if you want, this is called proper cluster in the terminology of Maggi, who is a specialist in geometric measure theory. We have here an infinite C and infinite C, right? So we have infinite lines here on both sides. So we are partitioning into 1 finite region and 2 infinite region, okay? And this is what I'm calling a new partitioning problem, because we've always looked at finitely many, right, region in 1 infinite. Now we're asking, actually, coming from this problem, well, what is the minimizer 1 fixed mass in 2 infinite volumes? Which is a bit difficult because now you're dealing with infinite length. Right, so it's going to be a local perimeter minimization problem. It cannot be global, right? Those lines are infinite. Those are, it turns out, yes. So it turns out the lens cluster is exactly, so this is an arc of a circle whose center is here. And the other one is symmetric arc of a circle whose center is here. That is the minimizer of, it's called the lens cluster. And we've been able to prove that the standard lens cluster is the unique, it's not easy, unique, locally, I said locally minimizing cluster for what we've called at this point a 1-2 partitioning problem, meaning 1 finite mass, 2 infinite masses. So we have an area vector, 1 infinite, infinite. That's what I call it, my new partitioning problem. And the other proof was followed by, suggested, in fact, by Frank Morgan, and relates to double bubble. So how does it relate to double bubble? Well, you see, you don't have to read all this. What you see is, yes, we know that we have a unique minimizer. If we fix mass 1, that's my mass, my small, and this is a big mass A, area, really A. We know that this is prescribed unique. And what we can see, perhaps you can see it easily, if I take this mass A tend to infinite, I make it huge, then it will converge to precisely half of my lens. What did I call it? Lens shape, right? And using the uniqueness of the minimizing of double bubble, we're able to show that the local minimizer for the 1, again, domain fixed in 2 infinite areas must be the lens cluster that I described earlier. Infinite line, that's not too surprising that your line would be minimizing, locally minimizing, plus this 2 shape of a piece of a circle. So I'm not going to give you ideas of the proof. Yeah.
So I think maybe Alina has the question. What are the central of these two arcs of
So you see, my pointer is not working very well. This is, this actually, I'm going to go back. This is the lens cluster. We can find, in fact, exact formula. Yeah, there's around 20 degrees. Yes, it's very helpful. It's very helpful. And we have exact formula for the graph. This is the graph.
The upward would be on the down, so at the center of the down.
So this is piece of a circle whose center is here.
Ah.
Yeah, and it's symmetric otherwise. Yeah, it's exactly that. So in fact, we started with the master students with calculus of variation classical. Assume it's a graph, assume it's symmetric. We're able to show exactly what the minimizer is. It's exactly that minimizer, and assuming it's a graph, etc. But it is the idea of Frank Morgan that allowed us to do it in general. And this, by the way, appeared just, not appeared, but was accepted just recently, the transaction of the American Math Society, which we were happy. Again, not on undergraduate, but master student, so obtaining nice results like this, it's nice. So now that I've introduced this new type of partitioning problem, let me finish with some conjecture that we've discussed. So this is the solution to one, again, fixed, called a proper cluster, fixed mass in two improper clusters. Well, what about two fixed masses in two improper clusters? What should be the minimizer of that problem? And so we are working on proving what we believe is the minimizer. So the conjecture for 2-2 cluster, 2 finite, 2 infinite, we suspect will look like this. Basically, you could think of it as a, yeah, we suspect. What's that?
You could have a shiny.
With two given masses. So in order to show uniqueness, you have to eliminate lots of cases like this. So this is 2 finite and 2 infinite. What about 1 finite mass and 3 infinite region? I'm leaving you some second to have the time to think, what should it look like? 1 finite mass and 3 infinite regions. So it has to be divided in 3, right? 3 infinite regions. What should it be? And here's the answer. That's our conjecture. We called the first one peanut and the second one Taylor's chalk. Taylor chalk to the tailors as the person who makes clothes. Makes clothes. That's our conjecture. And merci beaucoup pour votre attention.
So also in the Taylor's chalk, you have arcs of circles with
arcs of circle, yes.
Because this reminds me there is still an open problem in reality to prove that if you want to have an isoperimetric shape for shapes with a lower bound of the curvature.
Okay.
Positive lower bound of the curvature, convex, let's say convex, but lower like curvature, like then you should have some lenses. And this reminds me of this because you always have, then actually the conjecture is that I guess you get a lens with gamma curvature formed by 2 circles with 1/gamma radius.
Okay.
So
okay.
they're not necessarily centered on the opposite arc,
okay.
but
okay.
further apart, but the shape is very similar. So you have all the time things with 1 curvature.
Yes.
Or same curvature.
Yes, we are basing, to prove all these results, we're basing on regularity results that were obtained by Frank Morgan, but also Almgren and Gene Taylor, right? And so they are able to prove that minimizer must have fixed curvature, must have given angle condition. We are using all this to be able to prove our result. Yes, it is relying on lots of results.
Yeah. Very nice.
The uniqueness is actually the most difficult part.
Yeah, I wouldn't I don't have a good intuition about what the other term is.
Yes, the non-local term. So it's not here, right? It's not here. It's in the picture earlier. That's again, it's at the next order in the gamma convergence that it will tell us where those lengths must be located on the. And how many? Yes, all this will be determined at the next order, the gamma convergence, and we have result on the gamma.
J'ai une question un petit peu, comment dire, un peu hors du hors, qui ça porte au sujet, un petit peu, comment dire, risqué. Donc, on peut dire que, enfin, dans ce genre d'études, on peut imaginer le sang humain. Je sais pas.
Le sang humain en copolymère.
Non, mais comme polymère, je sais pas, par exemple, la façon dont l'hémoglobine se mélange à l'oxygène, c'est. Est-ce qu'il y a. Non, mais est-ce que tu as déjà pensé à des séparations biologiques?
Alors, ce que je connais en biologie, c'est des modèles qui sont pas de ce type, en fait. Je travaille aussi sur des cristaux liquides. Hein. Et les cristaux liquides, effectivement, ils sont capables de s'en servir, mais c'est pas la même application, en fait. C'est pour être capable de remarquer quand il y a des changements qui se passent. Là, on se sert de substances différentes qui s'appellent des colloïdes pour voir comment ça réagit. Et là, on peut voir, en fait, des senseurs, des façons différentes d'étudier le sang. Et, mais ça ne ressemble pas, ça ressemble pas à ça du tout. Non, non, c'est pas des problèmes d'interface. Ça, c'est des problèmes d'interface. Ce sont des problèmes au niveau de calcul des variations, mais pas du tout de cette structure. Donc, je ne connais pas, non, d'application de copolymers en...
Peux-tu dire quelques mots des applications biologiques? Donc, là, tu dis que tu utilises le calcul des variations. Et qu'est-ce qu'il y a?
Ce qui se passe, c'est il y a des défauts qui se forment si on a plusieurs, donc ça s'appelle des colloïdes. On met des structures dans l'espèce de cristaux liquides et ces structures créent des défauts. Et selon ce qui se passe dans l'application biosenseur, il va y avoir des changements de, qu'est-ce qu'on met, je puis dire, sur le bord de ces colloïdes, et ça forme des changements dans les singularités. Littéralement, on peut avoir des singularités qui sont des points, on peut avoir des singularités qui sont des lignes, et comment est-ce que ces lignes se rejoignent, comment est-ce que ces points se déplacent sur les colloïdes. Ça nous permet donc de différencier toutes sortes de structures qu'il y a dans le sang, grâce à ces changements topologiques, si je puis dire, sur les colloïdes. Oui, c'est ça. Ça, c'est ça. J'avais le choix de deux trucs, j'ai décidé, ça, c'est un peu plus colloque.
Other questions? No, let's thank you again. You know that Milman, they also worked with another type of mass with Gaussian.
Yes, they're using both, actually.
Yeah,
They are using the
exactly.
Gaussian approximation to prove that. Yeah.
If you look into other type of area measure, then just the back.
No, we have, let me.
Yes, yes. Go upstairs. Yeah.